Hi, in this video, I want to tell you a little bit about some properties of complex numbers that we will need for Fourier series. In Wednesday's lecture, we defined the product of complex numbers and what complex numbers are, that is some real number plus I times another real number. And we defined a rule for multiplying them by foiling this product with the convention that I squared is equal to -1. So in this case, if we FOIL the product, for the x1 term, we get x1 times x2 plus I times x1 y2. And if we FOIL the blue terms, we get I y1 x2 plus I y1 times I y2. Now, if we collect the terms that create the real and the imaginary parts, the real parts come from here, but also from here, because I squared is -1. So we get x1, x2, minus y1, y2. And then the imaginary part of this product will be the sum of the imaginary components of these two terms. So x1, y2 plus y1, x2. So that is the definition of product. We discussed some of the properties on Wednesday, and some nice ones are that if you take the product of two complex numbers, their length is the product of the numbers individually. And a consequence of that, if you want to find the inverse of a number, you can express it as z bar over absolute value of z squared. If you prove that, to prove that, you simply multiply z times z inverse, which is z bar divided by z norm of z squared. And by computation, you get that this is the same thing as norm of z squared, that is 1. So what I want to now talk about is we have to talk about functions, series, and integrals of real numbers, and I want to extend them to complex numbers, but in a fairly direct way. And the way to memorize it is be real. All of these things will be defined by first reducing to real things. So, say functions from R to complex numbers. These can be thought of as, because complex numbers are really pairs of real numbers, we can express them in terms of the components of that function, namely the real component, real part of f, u, and the imaginary part, v, of f, in terms of which f can be written as u plus iv. Now, this decomposition allows us to define all of the things that we would like. For example, continuity. F is continuous if and only if u and v are continuous. And this, you might recall that with this identification, another way of writing f is u comma v. So then f becomes a function from R to R2, and when is a function like that continuous? It's exactly when the components are continuous. This is a variant, or closely related to what you did on the exam, the second midterm. Now, what about integrals? If I want to integrate from a to b, f, and let's assume that it is continuous. Well, how do we define this integral? We express it as u plus iv dx, and we express this integral as the sum of the u integral plus the sum of the iv integral. This way, we reduce it to two real integrals, and if you want to define integrable, then you say that f is integrable if both its real and imaginary part are integrable. But mostly we will be talking about continuous functions, so all of these integrals will automatically be defined. And finally, we will need one thing about derivatives. And the derivative of f is, again, we take the derivative of u plus iv, and we know what is how to compute the derivative of u. the limit of the difference quotients, and then the derivative of v is just the same. All of this time, u is a function from r to r, and v is a function from r to r in this treatment. One remark is that if you have taken 132, or are planning on taking, in 132, often the domain is also complex numbers. And this analysis is different if you have functions that are complex to complex, because they are really a function of two variables taking values with two variables, u and v. The treatment is different because then you have to talk about partial derivatives. But for us, we only have a single derivative. A fact that we will use is then that you can generalize the fundamental theorem of calculus. So f prime g integral is the same thing as substitution ab of fg minus integral from a to b fg prime. This holds also for complex number things. We will see a use of it later. Now, what about series? You have a series n goes to infinity of Zn of complex numbers. Well, that series, again, is a sum of its real parts and its imaginary parts. So we have two series, and you can prove that this series converges. And what it means, again, whenever we say series of whatever object converges, it means that the sequence of partial sums as n goes to infinity converges. So that sequence of partial sums, which is has the real part, sum of xn, and sum of yn, converges if and only if, in the product metric, if the components converge. That is, the component series converge. Well, most of the time, we will do, as in real numbers, that we won't directly analyze this convergence, but we will use some tests. And the absolute convergence, just like for functions, the Weierstrass-M test, or for sequences of real numbers, like in 131a, is usually the easiest way to establish convergence. And this is, again, very similar to what you did in homework 1. So suppose we have a series of a sequence of complex numbers, or a series of complex numbers when we sum them up. If the sum of the absolute values converge, and this is now absolute values, these are real numbers, so this defines another sequence and the series thereafter. If this sum is finite, i.e. converges, then the sequence of partial sums of these complex numbers, it doesn't matter whether you start from 1 or 0, is Cauchy, and it converges to the infinite sum, which by convention is the limit of that whenever that exists. And, well, we can decompose into components in a unique way, xn plus I yn, where xn is the real part and yn is the imaginary part. And then we can use the simple bounds. The xn component is less than the norm of the Zn. And this bound is fairly obvious because absolute value of xn is less than or equal to, well, is equal to square root of xn squared. And this is less than or equal to square root of xn squared plus yn squared because we made the denominator bigger. This argument we've seen earlier when we approximate distances of product metrics. So what we get is sum of absolute value of xn is finite, therefore, because it is bounded from above by the sum of the absolute value of zn's, less than or equal to. Therefore, the series xn converges. And similarly, doing the same comparison for yn, we get the sequence of partial sums, yn converges. But then, because the sequence of partial sums of the complex series, whose real part is the sum of xn, and whose imaginary part is the sum of yn, then this sequence of partial sums converges to some value. which we call the infinite sum. And that is the end of the proof. So really, whenever you are doing something like a summation, an integral, derivative, or continuity, it really reduces to talking about the continuity, integrability, differentiability, or summability of the component sequences, x and y.